we worked on this groundwater model for the Meadow Village area here. You know, it's roughly underneath the golf course here, and found the aquifer to be connected to the West Fork Gallatin River. And this is kind of my prop for this talk, is groundwater and surface water, a single resource. That's the name of this U.S. Geological Survey publication. That's kind of the theme you'll see here with this groundwater model. And it was really nice to work in the Big Sky area with all the cooperation we had with Big Sky Water Sewer District to give us the pumping data, and then Gallatin River Task Force weather station for recharge estimates to the aquifer. And the purpose of the groundwater model is to, you know, our original stated purpose was to see, well, what's the capacity of this aquifer? Can we pump more out of it? You know, can more be pumped without sky falling? And what would that look like? And we're using a standard groundwater model, ModFlow 2000. It's a U.S. Geological Survey. It's a computer model that's going to try to mathematically simulate the aquifer and stream system. So with that, next slide. You know where we are. Of course, we're right here's the Gallatin corridor, and this is the Meadow Village area. Sorry, and so we'll zoom in on that area in the next slide. Just showing the topographic map, and a couple of things I wanted to point out. You know, the golf course is right in this area, and our model is going to be centered in that kind of section 36 area. But along the creek there's some marsh symbols, and of course there's a pond out in the middle of the golf course, and the one right out here by the road abutment. There's the sewage lagoons. But it's a little marshy along that stream, and so in the groundwater model we'll see some flooded cells, and that's just kind of showing that shallow water table condition. Okay, I think we can go to the next slide, and just I want to point out that the geology is complex in the Big Sky area. That's up at the top. You can see the folds bringing that Madison limestone and the Palisades up here. But in the model area, it kind of boils down to unconsolidated sands and gravels of both QAL as modern alluvium, and then QGO as glacial outwash on this map. And so it's just these sands and gravels sitting on top of a shale floor. And that shale is a Colorado group shale, which is known throughout Montana to be an aquitard. You know, water doesn't readily move through that shale. So it forms kind of a floor to this aquifer. And if you, so you can go, oh, and then the South Fork is incised down into the shale, which is shown by the green on this map. And so the South Fork is kind of separated from the West Fork and the Meadow Village aquifer.
Does that shale not go, it ends at the South Fork?
It actually, the South Fork is entrenched down into the shale. Okay. So it separates it from the kind of alluvium sitting up on the bench. So in next slide. Okay, so in terms of data for this model, this was a really interesting project because we had such well-defined data. In these red dots are all showing monitoring wells, many of them that we drilled and some of them that were already existing. And from the well logs, we can tell right where the shale is at the bottom of the aquifer. So we're able to map the shale bottom very well. And also, of course, the shaded relief here is from the LiDAR data for Big Sky, which that's that light and ranging elevation data that's very accurate. And we had these red wells surveyed, and the survey data and the LiDAR are spot on. They're like within a half an inch or less in terms of vertical elevation. So with that LiDAR data, you can really accurately position the stream in the model, and also all the wells and the data from those wells. So all these wells were instrumented with water level recorders for the years 2015 and 2016. And Ron gave us for the yellow, or the 5 municipal wells for Big Sky Water and Sewer District, and Ron provided those data every 6 minutes, whether the wells were on or off for 2015 and 2016. And then the weather station operated by the Gallatin River Task Force is right here, right behind us here. And also we did some stream monitoring of the West Fork, and we found Originally, there was an idea that the stream was gaining something like 12 CFS, but back when those measurements were made, it was before the ponds were aligned, so that might have had something to do with that large gain, but we never saw, and we actually went to the same time of year out and tried to measure in the stream flows to see if we could find that 12 CFS, and no, it's kind of like single digits, gains and losses is more typically what goes on. I think that's it on that.
So what do you take from the meaning of that? Is that irrigation is not affecting the stream, or?
The irrigation, you know, we had all these wells, the red instrumented, and what we see is that these water levels in the wells respond to snow melt and to precipitation events, like especially if it rains like an inch. But their irrigation, not so much. Like Ron gave us the irrigation data too, and he showed us north and south loops of the golf course. And when those irrigation events are happening, we don't really see a discernible effect in the well. So that's, and then even our, one of our hydrologists, Dean Snyder, looked at the ET and made estimates of how much the crops use, and it was almost spot on what Ron was putting out. Or, you know, Big Sky Water and Sewer District was irrigating. So it kind of showed that the irrigation is designed to just feed the plants, and it's not creating a big effect, you know, an immediate effect anyway, to the underlying aquifer. So I think we can go on now to the next slide. So this was just a map of saturated thickness. So it's really in this cross section here, it's the blue, which is, this is the water table at the top of the blue, and then the shale surface at the bottom of the blue. And this cross section is along that line right up there.
So the deepest section of the shale there is what, about 100 feet deep?
No, more like 40, 50, 60 feet deep up at the top up there.
Okay.
Well,
Oh, that's what those numbers are then.
and
Okay.
that's from the water table to the shale. So yeah, it might be 100 feet all the way to the surface, but the saturated thickness is what's mapped.
Mm-hmm.
So we tried modeling this all the way down to this line because this is a thinner zone, but as you can see in the cross section, it's getting very thin and it's tilting up at a steeper angle, and it became problematic. And so instead we had to cut this chunk of the model out, but even though we took about half of the original model area out, there's still 90% of the water volume is retained. So
Looks like a lake,
yeah.
essentially.
Yeah, and then to handle this part of the model, we just inject some water along the southern boundary. And we calculated how much based on our recharge estimates. See if there's
Does that
anything
tail
else.
off the same way on the A side? Well, the A side did tail off same way on the B side.
This is, as you can see, it's kind of almost vertically chopped off here. And in reality, this is greatly vertically exaggerated. It's about 5 times vertically exaggerated. And if you actually take it down to normal scale, the whole model is about the size of a piece of cardboard. You know, it's just
Sure.
very, very flat system. And so even though this looks kind of extreme right here, this is actually where that shale tilts upwards drastically, forming the palisades. And so it does just kind of chop off the aquifer along that north edge.
Kirk, where'd you get the LiDAR data for this?
It's available online from a source that I can send you the link to.
Yeah,
but-
if you would.
Yeah, and I think, James, wasn't that Kristen that? Oh, you're here now. So Kristen provided us that link, and we got the data to Paul, our GIS person, and he then processed it. And we might even be able, if you're interested, we could get you possibly his products.
Yeah.
But anyway, okay, I think that's all on that. So in the groundwater model, this is just groundwater modeling systems, just a software that runs ModFlow in the background, the computer program. And GMS uses these things called calibration targets. So in every case, when you see these on a map or a graph, the observed data, what we actually measured out in the field, like a water level in a well or a stream stage, is shown in the middle of a little hatcher. And then the green bar shows the difference between the observed and the model data. So it's just a little tool showing whether the model's producing output that matches or not. And if you go to the next slide, it'll show if the model goes outside the calibration bar, it turns yellow. So, and if it's twice the interval, it turns red. So this is just the tools or things you'll see in the next few slides. So you can go on and run to the next one. So this is now a map view of the groundwater model area. And the model has 30 by 30 foot cells, little square cells in it. And it's a simple model. It's just a one-layer model connected to the West Fork using what's called river cells and mud flow. And that's shown by these little X's going across here. And then these blue triangles are flooded cells. And there's actually a pond right under here. So that's why you see all these flooded cells there. And then here's the pond where we are now. You know, that's where we are right there. And then below the dam here, below the road, there's more flooded cells, but this kind of a more natural alluvial channel down below, and it's kind of swampy, like I said on the original map. There was marshy symbols. And when we first ran this model, I took the data from the 5 aquifer tests for the municipal wells. And those data gave us hydraulic connectivities. It's a property of how well rock can transmit water. And the values range from about 67 to 151 feet per day. So I thought, well, let's just take a representative. We'll start with 100 feet per day, mid-range value, and then use the storage coefficient from the 2 wells that had observation wells. And interestingly, storage coefficient was 0.032. And storage, like often for unconfined aquifers, we think in a range of like 0.15 to 0.0. You know, how much water you can hold in the sediment. So it's a little low, but it's still within the normal range for unconfined aquifer. And so using those values, it actually calibrated pretty well with everything put in. But then it wasn't perfect. There was a few more yellow bars. Here's one way over here at the edge of the model. But there were a few more yellow ones. So then I said, we used this program called automated parameter estimation, where it's a computer program that works with bond flow and other programs. And we just said, well, let's range it between 50 and 200 feet per day and just let the program optimize the solution. So that's how we got this really nice calibration. And the next slide will show the parameter estimation results. So now, if you can see the difference between the orange and the green, the orange is where the contours are a little more widely spaced, and the green is where they're more closely spaced. And that's just this optimization program. Then it just makes adjustments to hydraulic connectivity until it matches, gets the calibration targets optimized. And as you can see, it's just a range like 50 to 200 is the range I used. And in real life, hydraulic connectivity ranges over 13 orders of magnitude. You know, it's order of magnitude being multiples of 10. So it's actually a very narrow range compared to what it could be. So, any questions on that? All right, so I'm going to go to the next one, I think.
It flows easier through the green areas and less.
More so through the orange. The orange is the higher hydraulic connectivity, so it would move more readily through the higher hydraulic connectivity. And then here in this diagram, here you can see the model grid, those 30 by 30 cells, and I'm just in the software selecting a column in the model and saying, well, how much water flows through this? And you can get it from these numbers in here. And then you have to do a lot of conversions because everything's in feet and days in the model. But I work out that it's flowing about 1.5 CFS through the model, both whether you calculate it by hand or look at the model result. And that's all I wanted to say about this. Is the numbers are about right. They differ slightly, but
1.5 CFS through that entire section,
like through the aquifer moving through.
and that's 120 feet a day.
Oh, let's see, 1 CFS is cubic feet per second. I gotta think about that.
Well, I don't know how you have to take the area of the section. I'm just saying, you said before it was 100-ish feet a day of connectivity of water through that section,
Yeah,
and that results in only 1.29 CFS.
yeah, cubic feet per second.
I
Because
understand.
now that 100 was feet per day, and it's kind of a different parameter. It's not really a flow.
Oh,
it's
yeah,
just
yeah.
a property. Whereas here now, for comparison, the low flows in the West Fork are about 8 to 12 CFS in the late summer. So 8 to 12 versus 1.5 kind of going through the aquifer. So if you want to just have something to compare to. So, okay, yeah, go to the next slide now. So here was Ron's total pumping data for 2015 and 2016. And what we did is just boil down the every 6-minute data to daily values. And Ron helped me figure out how to do that using pivot tables in Excel. But anyways, here's all the pumping, and wells 4 and 5 didn't come on until 2016. They weren't running in 2015. So that's where you see the different colors at the top of this band. Notice they pumped a little more in 2016 than 2015. And these are the summer high pumping periods. And I got some numbers there just for comparing things. And let's see. Yeah, if they turned all wells on full blast, nonstop all day long, it could pump 2.2 CFS, but they're never really approaching that. This is, the most they reach here is about a little over 1 CFS per day. So the system's really only running about half, even at maximum rate right now, of what it could if you really wanted to open it up. So I started thinking of how to enter this into the model. You know, should I have a early season high pumping and then later summer medium? And as I thought about that, I thought, well, why not just enter all the data into daily stress periods into the model, because the software is supposed to handle it. And so that's what we did. So if you go to the next slide, this is now showing water levels in the wells. And this top and second well are at the far west pasture end of the aquifer, away from the pumping area. This well here is actually at the east end of the pumping area. So in this bottom graph, now remember, just those hatchers are just like on the map. The observed data is always the middle data in the hatcher, and then the model data is the other one. So here at the top well, I think you can see these are the spring snowmelt events. And even though the whole thing's offset a little, I think you can see that when spring snowmelt happens, both the model and the observed data are responding about the same. So that's showing that, well, we're at least pretty good in the ballpark in terms of our estimates for recharge, which again came from Kristen's weather station, because inadvertently their Big Sky or Gallup River Task Force gauge on the West Fork has this little arm that hangs out over the stream and measures stream stage, but also it created a great record of snow accumulation and melt. And so using the weather station data and that snow accumulation and melt, we could quantify how much water piled up in the winter and then melted. And so I took like 80% of that and used it as recharge. And so that's how we got the model to replicate the snowmelt events. And then same with summer precipitation. I just came up with a kind of a mathematical treatment of the numbers, because very low precipitation events, you don't see any response in the wells. Bigger events you do, so I came up with a mathematical treatment, just simple. But anything over, I think, 1 inch of rain, we added all of that for recharge and things like that. And then down here in the lower one, you can see the impact now of the pumping wells. And so when these wells are pumping high, it draws down water levels in the aquifer. But when you do the math on it, it's not drawing them out of sight. It's actually just, it's just stressing the system. But all in all, the system's reaching out to the stream. And that stream's having an effect. And you'll see that as we move on. This here was a leak in the irrigation system that got corrected, so we didn't try to model that. It was just a one-time event. Well, a couple times, I guess, but it got fixed. So we knew what that was.
It looks like the aquifer is recharging in September, though.
Where do you see this? Which
In both
year?
years. I mean,
Down
on the
here?
bottom one, yeah, it looks like in September it goes back up after the irrigation season.
Yeah, it's like once they shut down, well, lower the pumping rate back to winter
But-
levels,
Right.
yeah, then the aquifer recovers relatively quickly.
And we don't typically get a whole lot of rain in September, so
No.
it's not that's causing the recharge.
Generally not, although, yeah, you'll see some more interesting things as we move along, so we can go to the next one, I think. Now, here's just 3 more wells, all closer to the pumping center. I got kind of notes here for those of you that know the area real well, you can probably figure out. Like this one is, this is Creel Ranch, so this is right at the old Creel Ranch house there. We put in a couple wells near the stream. And so that's right below the pumping center, so that was a neat one to see. And I don't think I have, because I want to show you the next things more so than even these. But anyway, I thought we captured, it looked like the model's capturing what the system's doing reasonably well. So let's go on to the next one, Ron. Okay, so then, yeah, working with the daily model, I got to thinking, well, this is a great tool, but it could be really difficult to use this tool for certain things. It might be handy to have a monthly model. Ron, if you could toggle back and forth just from the previous to this slide. I just wanted to show that you can see it's the same solution, it's just portrayed differently in the monthly and daily values. Can you toggle? Yeah, so for a lot of purposes, the monthly model might be an easier tool for us to use in the future. So after that, then you can move on. Okay, so now this is moving to just 1 year at a time. So this is the 2015 data, and the black is showing the total of all 5 wells pumping, and then the blue is, it's not the flow in the West Fork. I want to make that clear. It's just the model computing how much flow is going from this small model area. It's like 250 acres to the stream. So what the big spikes you see are, here's the snowmelt event for 2015, and in the model I injected that over 8 days because that's about how we saw the wells respond, and that's about how long it took that snow to melt in the spring. So that's the biggest recharge event is the snow melt, and so when that snow melts, it goes into the aquifer, wells respond, and then that water, once it's in the aquifer, is driven in the groundwater system towards the creek. And that's really what the blue line is showing is calculated groundwater movement to the creek. And then 2015 had some nice summer precip events. In fact, you mentioned September. This year, there just happened to be a nice precip event in September. And so, what you see here is this is the low winter pumping. And then when it goes up in the summer, so there's that same high summer pumping period, then you see the gains diminish going from the model area to the stream to almost nothing and maybe even a slightly negative value. But remember, in terms of values, 50,000 cubic feet per day, which is that's what we're using in the model, is only 0.6 CFS. So thinking of late summer flows in that 8 to 12 CFS range. I mean, it's an impact, but it's somewhat modest. Only half a CFS versus 8 to 12 CFS. So now remember the next year they're going to. Oh, and you can see that the monthly. This is the monthly version and the daily version. And you can just see that the monthly version shows the similar results, just portrayed differently. So then go to the next one, Ron, if you would. And then in 2016, then there was a little more pumping. There wasn't so much relief from precipitation in the summer. And so on this year, we actually get a little more firmly into the we've lost those gains, and the stream's actually losing a little bit of water. But again, at it'd be in like 0.1 to 0.2 CFS range compared to 8 to 12 flowing in the creek in the late summer. Now, often at the end of June, West Fork is still flowing about 30 to 40 CFS. So So really, the early part of the summer is probably not a big issue. It's just that very late summer is the time that you want those water conservation efforts to kick in as best as possible. So, any questions on this? Or okay, and then there's the recharge in the spring again. And then,
So we don't have any weather or climate data that says, was 2016 a drier than normal, or whether it average, or,
Oh, we probably do. I just haven't
Yeah.
dug that up and actually charted out how these 2 years compare to the global scheme. But I think they were both not extraordinarily unusual. I mean, we had nice snow melt. Snow melt varied. Like one in the first year it was in March, and the second year was in April. So, you know, and there's one difference right there. There's different snow melt.
yeah, I don't know anybody who really collects weather data in the meadow here, because, you know, our weather is so much different than the valley, for instance.
Yeah, but Kristen
We've
has
got a weather station at the
Okay.
shop that is real time, so we've got it goes over to MSU, so we've got all that data. It's like Kirk says, he just hasn't
Yeah.
overlaid it on top of it.
Yeah, I just haven't compared it to like the 30-year. But I mean, I don't think there was nothing really that struck us as that either one of these 2 years was like way out of the extreme. James is shaking his head because James has been working up climate data for the bigger report. And
Okay.
it was just, you know, it was just that they pumped, you know, there was less rain in 2016, so they pumped more
Mhm.
water. You know, there was probably more need on the golf course. And that's just a little less relief to the whole system. when
Just-
you don't get those
Just to
summer-
clarify that comment, so the wells that Kirk's plugged into this model are the domestic drinking water wells that provide irrigation for all the homes, businesses, and condos. All the irrigation water comes out of these ponds. Okay, so the pumping of this is a function of irrigation around the golf course.
Oh, yeah.
The golf course irrigation is coming from these sources here, but they kind of go hand in hand. You see more irrigation
When it's
demand
dry,
as the
yeah.
golf course demand goes up. But I just
Yeah.
wanted to clarify.
Yeah, thanks for
Yeah.
doing that, because that's an important point, yeah.
Yeah.
And, so, yeah, you can probably go to the next slide now, because I got just a couple more things to show. And just, it was kind of interesting looking at the numbers. This is showing the end result of the 2-year model run. And so you just see like very large numbers, so these are feet cubed per day. But what I wanted to point out is if you look at the daily model versus the monthly, all the numbers are virtually the same. There's slight differences. It's a different calculation, but they're virtually the same except storage in and out, and that's just because the daily model's computing all that daily changes in the pumping rates and daily changes in stages in the stream. Even the recharge is handled on a daily basis. So there's all this water going in and out of the system, but when you look at it from a monthly perspective, the daily data just gets kind of washed out. So even though so for certain things, the monthly model, this is just showing that the monthly model is accurate and will give you the correct results, unless you're interested in that, what goes on a daily basis. So then this is I got one last element to show, and this is interesting because like when you do aquifer tests on wells, you turn the wells on and you run them like full blast for a day, and then you shut them off and measure recovery. And as groundwater hydrogeologists usually think that after 1 day of recovery, it should bounce back to where it started from. And so this is showing all 5 wells in the model pumping for 1 day full blast, 24 hours a day for 1 day. And so it draws water levels down many feet. These are in feet. And it draws them down about 6 to 12 feet right at the wells. And that's very close to what, if we look at the aquifer test data for these wells, it's right in the ballpark for what are in those data. Now, then in the model, I shut the wells off and then look at it a day later. And if you go to the next slide, it'll show that result. And so there is this residual drawdown, but it's largely recovered in 1 day. And then go to the next slide. This will show 2 days out. It continues recovering. And so that's the whole system kind of responding, because the initial cones of depressions bounce back, but then there's kind of a system effect. And the next slide is going to show how the stream was affected by that 1 day of extra pumping. And So, because there's a normal winter pumping rate, remember I said 2.2 CFS is the most they can pump all day. So the added rate is 1.76. So that's what this graph is showing, is how the stream flow gains responded to that 1.76 1 day of pumping. And as you can see, it never even reached a quarter of a CFS impact to the stream. But it impacts it for many days. It actually takes about 2 weeks for the system to recover. And that's the aquifer reaching out to the stream and recovering that 1 day's worth of water that was pumped. And so that just kind of shows you, that's kind of what the model's telling us this system behaves like. And so I think this is a nice tool now that, in the future, you could actually take, real-time data in the midsummer and plug it in the model, just use the same calculations I used for recharge, and plug in that year's pumping data and see where you are on those graphs. And, just decide what that means. Should we cut back on pumping, or is everything hunky-dory, or what?
How often do we pump all those wells?
Well, in that data we had from 2016, they were never pumped.
Yeah,
full
we don't.
blast.
We don't hardly ever have all 5 wells on
Yeah, we
simultaneously.
approached about half the total rate, like about 1.1 CFS versus 2.2 being everything's on all day long.
And we don't ever run everything all day long, do we? Not even in August?
Year. Well, in 2016, we ran the 2 new extra wells. Somewhat, it was a dry year. 2007.
But all day long?
No, they're on an automatic call. But 2017, they never turned on. It's all based on the demand and the tank.
But
2018, we did turn them on.
that's the benefit of having the 2 new wells. Before that, you were on the ragged edge with all 3 wells.
The gas pedal was smashed to the
Right.
floor all summer long.
Yeah, so it was a game changer for us having the 2 additional wells.
Yeah, and I don't know if you need to go back to that pumping graph or anything. It just showed that 2016 data. But anyways, yeah. So I just think the tool will be handy to use. And Ron's got a consultant in Bozeman that runs ModFlow and has done it in the past, so I'm sure he can pick this up.
And we're gonna get the model as part of this, which is fantastic for us going forward, so.
Yeah, our whole James is gonna work on the whole Big Sky report. He's gonna talk next if you got time still.
I got time if,
Yeah,
yeah.
there you go.
Yeah, come on up. It's just
James-
gonna be like a 10.
So
15
you
minute.
see preliminary on everything, and so the goal is to have all this as final report by year end before you retire?
Yeah, the modeling's pretty much is done. We'll have somebody take a look at it, like our other modeler or two, and just to verify that everything's okay. And then, we'll be writing the report in the next few weeks. And then I got a lot of, I have 40 pages of documentation of how I did all the work, so all I gotta do is extract out of that and put it into kind of a more final readable document. And it'll have